Hello. Hi, everyone. I hope everyone's having a good day. Today, I want to try to progress on what we did last time. So, we created a simple animation of the ball just bouncing around using uniform distribution, and it didn't look really fun. So, today, I thought, can we try to maybe use some of Newton's laws to try to create a parabola? A parabola, if you've never heard of one, is literally something that looks like this. And what we're trying to do is try to model each of the position of that ball across that curve. And a really clever guy called Isaac Newton came with some laws of motions that enables us to pretty much tell you what that position, given the initial angle of the launch, you can pretty much tell where the ball is going to be at any time, at any position in the space that we are looking at. So we are looking at a x and y 2D space. So we need x and y here, and we need to break down the velocity. And here it's going to be a vector. So it's going to have an x component and a y component. And that is what the first two equations here tell you. The first two equations are literally, if you think about it as a right angle triangle, you have your y component, which is v naught sine theta, and you have your x component, which is v naught cos theta. So once you have the x and the y components, you can take that, literally it looks like this as the initial parabola, and then you're going to literally take that x and velocity vectors and put that into your position coordinates. And that's given here. It comes from the pretty famous second law of motion from Newton, and it basically tells you S equals half ut plus half at squared. The A here is our gravitational force of the Earth for the y coordinate, and you don't have a y acceleration in the x coordinate. So it's a very simplified equation, and we can really just substitute these terms into the other ones, and you get your velocity equations, and then you can get your corresponding position equations. So what we really do here is if we look at the code itself of try to initialize some parameters. You have your gravity, velocity, launch angle. You can change any of that. But for the purpose of this demonstration, we're going to calculate using those initial vectors. And if we now jump to the code, if I just go to the code, hopefully you can see this. Um, so yeah, so we can run the first libraries that we need like last time. So we're literally going to use the same code from last time on how you can do animations. The only thing that's changing here is our x and the y coordinates from our last video. So let's take a look at what happens if we run this. Yeah, so that's gone through fully. If I quickly explain, so we're setting up some initial velocity vectors, and as you saw in the previous equation, we're using the cos and the sine, and then we have our initial vectors that we store, positions and the velocity vectors. And then we're going to run a loop across different time points. The time points are going to be from 0 to 10, sorry, 0 to 100 by a certain time interval. And we are going to update our velocity vectors initially using the initial equations we saw. And then once we update those, we're going to plug that in into our position vectors in the second set of equations we saw. And we're going to run through the whole time vector, and we literally get our x and y coordinates. Now that's the difficult bit. Now we can save that data as a data frame, and if anyone's interested how it looks like right now, the data itself, we have, as you can see, at time, position x and position y. As you increase your time, you can see it going x going higher and higher all the way to 353, and the Y gets the highest somewhere along here. So that's its highest position in the air, and then it just comes down. So we're going to try to plot this using ggplot, using the same animation we discussed last time, transition time, and that should give you a animation. If I press P, it's going to render all those different plots together. Let's see what happens. And there we go. So we've got our plot, which literally is a bouncing ball, but this time it's following the equations of motion, which is a parabola. So I hope that was interesting. It's pretty much the first time I've done something like this in R, where you're trying to model physical equations in R. Usually you use it for, you know, simulating data from distributions or running samples and creating sample distributions. And those are the kind of simulations you do in R, right? And this is pretty interesting to me. Like, I think R has most of the capabilities to do maybe pretty hardcore mathematical modeling. I mean, this is something I hypothesize could be completely wrong, but so far it's looking pretty good. I mean, I want to try to maybe take this next step further, maybe try to see if I can put this ball on a slinky or something and see if it can, we can do a simple harmonic motion maybe, see how that would look. So I hope that was interesting maybe for some of you. If not, then thank you for listening and see you next time.